Thank you. Can you hear me? It's working, right? Okay. Before I start, we'd like to thank Stefania, Giuseppe, Claudia, and David for for the invitation to give this talk. And this talk is mainly to find a way to maybe inspire you and keep working in this very exciting field. No? Then I am I am talking about the original neutrino masses. Um, the main You know, the main thing is that for a long time, we know that neutrinos are massive for a long time, and we have basically no clue about what is the original neutrino masses. Huh? And we would like to really know how to test the mechanism. Huh? The Brown-Engler-Higgs boson was found at LHC. We know this is something real. We know how electroweak symmetry breaking is working. However, we cannot explain neutrino masses what we have in the standard model. No? And again, for a long time, we know neutrinos are massive, and we have no idea what is happening. Okay, and it's a really very important motivation to go beyond the standard model because it's something real. Okay, that we know about. Now, this is the kind of idea I want to give you. I will show you what are the leading ideas that we have for neutrino masses, and we'll try to tell you when we should get Dirac or Majorana. And in this school, you talk a lot about neutrino resolve beta decay, which is we call this a rate process, which is crucial to know what kind of neutrinos we have in nature. No? And I will tell you a little bit about what kind of signature you can maybe have to be able to test the different theories. And I don't have time to talk too much about other things, but maybe at the end you can ask me. But this is the overview that I wanted to give you. No? Then, you have seen this for a long time. Neutrinos are massive. We don't know we don't know what kind of a spectrum we have, the normal order or inverted order. But what we see is that the masses are really tiny, below the EV scale, where all the other fermions are way far away when you think about their masses. No? And this is something that you have to take into account when you try to explain their masses. No? Now, let me go back to very basic things, okay? I know maybe you are too tired after this school, but let me go very basic things, okay? In the standard model, you have the gauge group, and you have the three different multiplet. In this case, the electronic doublet is in the fundamental of SO2, and this is the hyperchar. You know how they transform, and we have three families. We don't know why. And you have the right-handed multiplet, awesome, which in this case, of course, the right-handed multiplet, they don't transform under SO3 and SO2, they have hyperchar -1, right? And for a long time, we know how to give mass to the charged electrons, right? Weinberg did that even in the original paper, right? What we do is that we write the Yukawa coupling. This are the family index. This is the electronic doublet. And this is a standard model Higgs with ER here. Everything is here SO2 cross U1 invariant. We don't have to speak about color because they don't feel the strong interaction. And this is the Higgs doublet, okay? Where, the hyperchar is 1/2, and it's, of course, in the fundamental of SO2. Using that and doing electroweak symmetry breaking, the neutral component will take, that field will take, the field will take values very close to a constant field configuration that minimizes the Hamiltonian on the whole theory. And this, once you do that, we know that you choose a very peculiar vacuum configuration, you break the electroweak symmetry breaking, and that is enough to get masses for everybody, for the charged electrons here, right? And the Higgs, the neutral component, which is the physical one, also talk to all of them in the same way. And it's the same with quarks, right? It's amazing that only one Higgs doublet can do the job for all the charged fermions in the standard model particle physics. Then you get what we call the masses. This is the mass matrix. You can go to the physical basis when you rotate the E left and ER fermions. These two matrices are defined in such a way that you can go to the physical basis, and you get your masses for the electron, for the mu, and the tau. And the coupling of the standard model Higgs is following the sensing. It's proportional to the mass. And the same is for the quarks. It's a very hard prediction you get in the standard model, and it has been tested very well. And then, this is what you have. These are the electron mass. We know we can get the charged electron masses from the experiment. We know what is B combined in different experiments, and then you can find the Yukawa couplings to do the job, okay? The standard model doesn't explain their masses. It only provides mechanisms to say that they can get mass in this way, because the standard model doesn't explain the value of the Yukawa coupling. But it's good enough to explain how they are getting masses, okay? But the neutrino, they don't get mass, because there is nothing that you can write down at the renormalizer level that allow the neutrinos to get mass. And then this is a hard prediction of the standard model of particle physics that are massless. But we know this is wrong. Okay? Then when you check, there is a symmetry that you know very well, that is lepton number. You can actually write a global symmetry you want for every flavor, but we know today for neutrino oscillation, this is not a symmetry anymore. But the total lepton number is actually accidental global symmetry in the standard model. And this symmetry is accidental because you didn't put in the beginning, you just use the gauge symmetry and the multiplet, and you realize it's a symmetry. And it's a good accidental symmetry only at the classical level. This is a little bit theoretical, but they are, effect. They are called SO2 instantons. That actually you can show at the quantum level the symmetry is not really conserved, but the violation is really so tiny that for any practical thing, at least any experiment that we worry about for neutrinos, the symmetry is a very good symmetry. And it's key because we'll tell you if it's Majorana or it's Dirac, okay? Now, again, the question that we have to think, is how do we get mass for neutrinos, no? Even if people have been thinking for a long time, we should try more, especially young people, no? Now, the neutrinos, they can have two different personalities, as you know, right? They can be Majorana, means that somehow you have to generate this. The key thing here is that this lepton number has to be broken in two units. Then if you write a theory where lepton number is broken in two units, you should be able to get Majorana masses for neutrinos. If it's conserved, they will be Dirac, okay? Then since the symmetry tells you what kind of mass matrix you will get for neutrino, you should follow that symmetry and see what is happening in whatever theory you want to write for any reason, okay? And what you get depends a lot of the theory and the degree of freedom that you get, okay? But again, lepton number, total lepton number is a key symmetry you should follow. Now, let's talk about Majorana. How often you can get Majorana, okay? I will need many hours to talk about all the mechanisms that we know from Majorana, but at least I would like to mention here. You saw this in the previous lectures, and we have a lot of theories that have been written in physics beyond the standard model, like left-right, Patti-Salan, grand unified theory, where typically you get Majorana. I don't have time to talk about all these things, of course, but it's good to know. I would like at least to mention that there are a lot of ideas that you could learn about. Now, imagine, again, forget everything that, forget everything and try to go back to the standard model again and ask a very simple question. You can ask the question, can I add just one field, only one field, to the standard model and be able to generate masses, Majorana masses for neutrinos? The answer is actually yes. It's what we call type 2 SISO. This is a field, a delta field. Oh, sorry. It's a delta field that transforms in this way, that under SO2 will transform in the adjoint representation. And then if you put how L transform, the lepton doublet, you can write something that is gauge invariant. Now, this field is a very peculiar field, has single charge Higgses, a neutral pair, and a double charge Higgses. Okay? You can check at the same time that apart from that term that I wrote, apart from this term that I wrote, you can also write down a term with the standard model Higgs like this. And then this means that the presence of both interactions, I tell you, lepton number is broken. Okay? Then you can give a vacuum expectation value to the neutral component of the delta field, and you will get a mass that is the Yukawa coupling, Majorana mass. This mu parameter here, the vacuum expectation value of the standard model Higgs, and the mass of the new triplet. Okay? And it's a very simple mechanism because what happens again, you take the standard model, you hit just one field. It's different from the other fields, but it's just one field. Has more degree of freedoms inside, but it's just one scalar field. Okay? Now, the theory doesn't really, the model, or I would say the toy model, doesn't really predict anything because you don't know what is mu, you don't know what is the mass of this scalar field. Then, however, you can study a little bit. You can realize that maybe if the Yukawa coupling is order 1 and the mu parameter is order the mass of the Higgs, you will get very depressed. Because if this is the case, this new Higgs, the mass is very, very, very high. And then you start getting depressed because we know how the standard model works, and we will have to have a mechanism that allow you to test, to be able to test. We don't have any experiment to go at this energy and test, okay? But since the theory doesn't predict, maybe this new Higgs is a TV scale, and the mu parameter is small. For people that worry about theoretical issues, it's actually this mu parameter is protected by lepton number of B minus L. Therefore, maybe we can have this mechanism for neutrino masses, and this new Higgs is light, and we can look for them at collider, maybe, and then we can test. You see, when I say maybe, it's a little bit depressing because I would like to be able to write something that I can make a prediction, but here you cannot make a prediction, okay? Then you can study carefully this type of a scenario, and what you can find is that, you will have a neutral Higgs, that is the standard model like Higgs, and then you will get other Higgses. But don't pay attention too much about them. Pay attention to something very exotic. There is a double charge Higgs that coupled to leptons. But the beauty of this is that when you write this in the physical base, this coupling, the coupling is defined by PNMS and the ion values of the neutrino. Therefore, if we put all the neutrino, all the information we know about the mixing angles and the ion value of the positive value for the ion values, you can actually predict this coupling very well. And you can do something similar for the single charge Higgs. Then, if this is light, you can actually produce at the Large Hadron Collider, okay? Because it has electric charge. You can produce through the Z and the photon, okay? And this is what you can do. But before that, I would like to remind you that, every time you give neutrino mass, you will get the no trivia PMS. And I just wanted to remind you that this is the same PMS as in the previous, okay? Now, as I said, imagine this is a mechanism that we have for neutrino mass. Imagine. How to test that? Well, you can produce at the Large Hadron Collider. You can make that calculation, the cross-section versus the mass of this new Higgs. Even if you have, a Higgs, if the Higgs is like below 500 GeV, maybe the cross-section is large enough to see something. Okay, this kind of a number, 500 GeV. You can study something, you can produce, and you can watch all the decays. These guys can decay to 2Ws, can decay to charged electrons, can decay to the single charge Higgs and W. Assume for simplicity that you are getting, let's say, 4 muons. It's a pretty clean signature, no? Then you can estimate for a given luminosity, you have the brushing ratio, and you have the charge Higgs mass. Then again, if you are below 500 GeV, maybe you get enough events to see that. Okay? But already you see, it's not that you have a huge production cross section, right? But maybe there is a way to see multi-muons, a collider, and in particular, the energy, the invariant mass of two muons will give you that particular Higgs mass. Therefore, if you study carefully this type of channel, maybe you could see that, okay? There are a lot of experimental bounds on that. I will not tell you too much about this, but something that is actually very beautiful here is that, often we talk about doing neutrino experiments to know about the neutrino spectrum, right? Which is very important. We need to know if it's a normal order or not. But if you find this Higgs decays, since the coupling, the physical coupling of the double charge Higgs and the charged electrons is defined by the PNMS matrix and the eigenvalues, values, you can show that the branching ratio of the double charge Higgs will be mainly to muons and taus if the neutrino spectrum is normal, and will be mainly EE and also a large branching ratio to mu and tau if you are in inverted order. Therefore, not only you could, if they are light, you could produce, you can watch all the decay channels, but if you are lucky enough, you could see the different branching ratio and get what kind of neutrino spectrum you could have. This is like a very happy, a scenario. You can ask me, later how I can depart from that, okay? But this is really something spectacular. Regarding what you have been seeing in the school is that you have the usual contribution to neutrino resolve beta decay because, you are generating Majorana masses, right? And you are generating a new contribution to neutrino resolve beta decay due to the fact that the double charge Higgs coupled to two leptons, okay? However, this Higgs has to be heavy because there are collider bounds, which you cannot be too light. And therefore, this is highly suppressed, and the usual contribution to neutrino beta decay will be the dominant one. Then if you find neutrino resolve beta decay, there is a good chance that one can match things, to a mechanism that the neutrinos are Majorana, but due to the fact that this is suppressed, this doesn't mean that you cannot see a collider. You could see a collider, still be consistent with all the experimental bounds that you have been discussing in this school. And on top of that, you could maybe learn more about the neutrino spectrum and other things, okay? Again, if this is the mechanism for neutrino mass, if this Higgs is light, okay? We don't know. Now, I will now mention the standard mechanism that you are familiar with, which is you can add new fermions, at least 2 copies of them. I will use, for me they are left-handed here. You can use this identity if you want, right-handed neutrino. And you know this very well. You can write a mass for these new neutrinos. We typically say singlet or right-handed neutrinos, Yukawa coupling. Similar to this, the presence of both interactions tells you electron number is broken explicitly. And you can get the mass matrix. This is something that you saw in the school very well. And you can get, here M Dirac is a usual thing. You can get that the mass matrix for the light neutrinos is suppressed by some MR scale. And the heavy ones is suppressed. Again, this is a really toy model. Often we pay too much attention to toy model. This doesn't predict what is MR, doesn't predict what is M Dirac. Then we just can say this could be a consistent scenario to explain why neutrinos are light because this MR is large. But in reality, doesn't really predict any value, okay? Then we don't really know what the mass of them are. You can define the physical states, and again, if you're not lucky, and this M Dirac is electroweak scale, you will get very suppressed because everything, the mass of these new neutrinos are very, very high. Then there is no way that we will see that. Maybe this is not the case. MDIRA is not predicted, could be smaller, and maybe these neutrinos could be lighter, okay? You have lectures about how to look for them, but let me make a short summary about, again, there are many mechanisms for neutrino, binary neutrinos. These are let's say, the simplest one, okay? The only thing you can say is that you can build a mechanism with a new Higgs that gives you that the mass matrix for neutrino is suppressed by the new Higgs masses. If this guy is heavy, you could say, okay, this is, neutrinos are light. But again, the mechanism doesn't predict the masses. You have to be very open-minded here. The same for the so-called type 1 CISO. The mass matrix that you get is suppressed by the IMR scale. Again, it's not predicted. This is a toy model. You have to be lucky that this is not very high, and this is the case, no? Then if you write the mass matrix for the neutrinos in this way, a la Weinberg, it's electroweak scale squared divided by lambda, you can see the different suppression scales, right? In this case, lambda for type 2 is basically this ratio on this. And again, let me emphasize, when you do experiments, you have to be experiment. You have to be optimistic. You have to look for what you can and be, pray to be able to see a signature. But as a theoretician, I have the responsibility to tell you we are not able to predict these things, okay? And this is a sad story, okay? Now, if the neutrinos are Dirac, you should not get mad, okay? Okay? Maybe they're Dirac, and you have to live with just this interaction and small Yukawa coupling. There isn't nothing wrong with that. Often you see many weird statements in papers and things like that. There's nothing wrong with that. The question is, how do you write a theory that you can predict Dirac neutrinos? This is a different story, okay? But there is nothing wrong about that. Then here is 50-50, okay? Could be Majorana, Dirac. We don't know. Only experimentalists can tell us what to do if you make a discovery. Clearly, the fact that this Yukawa coupling is very small, it's not so easy to have access because still we discovered the standard model Higgs and we are not able to measure the coupling to the electrons because the coupling is so tiny. We need new colliders to be able to go there, okay? Then, we are talking about 10 to the minus 12 here. Now, this first part is about which are the toy models that we have that has been discussed for many years to give Majorana masses. These are the properties. In the case of type 2 CISO, if this is the mechanism, there is maybe a way to find these new charged Higgses, doublet charged Higgses, because they are very exotic. They give you signature collider, electron violation collider, if they are light, if they can be produced. In the case of type 1 CISO, the right-hand neutrinos are singlet. Then to be able to produce them is really hard because you have to use the mixing with the standard model neutrinos. And this mixing, we don't really know. You have to assume that maybe they are large enough to be able to produce a collider. Or maybe once you have right-hand neutrino, you can gauge B minus L. And this type of theory will give you a new gauge boson that allow you to produce then a collider. But again, this is just a toy model, okay? Now, let me go now and tell you why most of the community for a long time believe that neutrinos are Majorana fermions. And you will be happy because if you're looking for neutrinos of beta decay, you say, okay, I hope that they're right. But wait a second, okay? Then this idea came out actually here in Italy when Yogesh Pati was visiting ICTP in Trieste and talking to Andu Salan, the same father of the standard model. And they ask a very simple question. They say, why you have quarks and leptons? Why we don't unify them? And they're just fermi. It's a very simple idea of quark unification. But once you do this, we have a symmetry for quarks, which is lepton, a baryon number. For leptons, we have the lepton number. Once you put them together, you are breaking explicitly lepton number. Then generically, you should be able to get, if this symmetry is broken into units, you should be able to get Majorana neutrinos. Okay? But this is 50 years ago. Okay? I was born already. People were talking about, but this is the first theory that was written. You just pay attention to the SO4 symmetry. Look what you do. You have, in the standard model, you have the different multiplet. You have, you have a quark doublet that transform like this. You have UR, which transform like this. You have DR like this, and then you have the electronic doublet that that is transforming like this, and the ER. And the question is, how do you unify this in one multiplet? Don't forget that the quarks, they have color, then they have internal quantum number. Then you can put 3 colors. The 3 colors you have, wing a new, we call a new, using the SO4 language, a new color, which is electron. Okay, and then you can define a theory which they actually know electrons and fermions. At the scale where you have this SO4 symmetry, they are just fermions. They're just a multiplet that describes spin 1/2 fields and nothing more than that. So for us, this is very important because this is the first idea we got in the field. It's actually the first theory that was written in physics beyond the standard model, in the history of physics beyond the standard model, and already they are predicting right-handed neutrinos because you see that I can have QL and L, but I have only 2 right-handed multiply here. I am missing something with right-handed. Therefore, I need this right-handed lepton there to be able to complete the multiplet. This is the first prediction that we have to predict right-handed neutrinos. And the idea is matter unification, even before full unification. This is a problem because, it's not a problem, it's that this theory will predict, this is a seesaw relation. This theory will predict that the M Dirac is the mass of the out quarks because they live in the same multiplet. Think about the top quark, 173 GeV. If you put that, the only way to get masses below 0.1 eV if the scale is very big. Therefore, it's very beautiful, the idea theoretically, but the seesaw scale has to be 10 to the 14 GeV. Often people celebrate that. Even if I am a theoretician, I find that's very beautiful but depressing because I want to write a theory that can be tested. We don't worry about testability of theories. I don't know how long you can do this in, every day, write a theory that never can be tested, and there are no rules. Nature, you don't play with nature somehow, okay? But this is what Patti Salam predicted, was the first theory, matter unification, predict right-handed neutrinos. Since you're predicting this, you need to do seesaw, and everything's happening in the high scale. You could see neutrinos of beta decay because the neutrinos are Majorana, but you will not have access to the mechanism that is explaining neutrino masses. You cannot produce these new gauge bosons in SO4, you cannot do anything. Then, however, I will try to be a little bit more optimistic. With my collaborator, Mark Weiss from Caltech, we studied this carefully and tried to find a way out of this argument, which is a little bit tricky. Then if you consider, SO4, basically you have QCD, SO3, and then you want to build a theory that has SO4. And it's a simple extension of the then basically what you're making here is that you unify QCD with B minus L, and the rest are details that you don't have to worry about that, okay? And then you can write a different representation. Right-handed neutrinos is here, a different notation because everything is left-handed here. And then you can write a theory that is even simpler than Patti Salam because Patti Salam has SO2 left, SO2 right. You don't have to worry just about SO4 unification, right? Then this means that you have this symmetry here. You can break the standard model, and you can see what kind of prediction you have. Again, but if you have normal seesaw, the regular seesaw, Still, you are predicting that the M Dirac in the mass matrix for the seesaw relation is mu. Therefore, you have to find a different type of seesaw mechanism to be able to relax. And maybe you can do seesaw mechanism at the lowest scale, and you could dream about the stability. Here, since you have SU4, you have the gluons here, a new lepton quarks. We say beta lepton quarks. They talk to quarks and leptons. Doesn't matter. But what you can do is actually, you realize that if you add new fermions in the theory, this is something you saw in the school, it's called the inverse seesaw mechanism. You can build a seesaw mechanism that was explained in the lectures that has this particular relation here, where there are these zeros. Typically, people put these zeros by hand. Here, the theory tells you you cannot write any mixing between the different components. These are the standard model neutrinos, right-handed neutrinos, and these are new singlet. If you do that, inverse seesaw allow you to have very light neutrinos, even if these mass matter here are large. Okay? And therefore, you can actually have quartet unification at the low scale, because mu can be small, and you can explain why neutrinos are small, and you can break everything at the low scale, and then you can dream about the fact that you can maybe test this at colliders. Okay? However, not too fast, because there are ray processes here that tell you that these Bertoletto quarks that live in SO4, they give you a lower bound that is around 1000 TeV. Then the quartet unification is happening at, let's say, 1000 TeV. Maybe some of the fields could be lighter and can be produced at the LHC or other colliders. But you cannot, generically speaking, you cannot go below 1000 TeV. But I mean, 1000 TeV is way smaller than 10 to the 14 TeV, GeV, right? Therefore, from being depressed, you become maybe a little bit optimistic. And everything is consistent with everything, you know. There is nothing that you cannot be consistent, but you have to be honest that these bounds are hard bounds, and they give you 1000 TeV. Unless you play some, I personally don't like to play weird things. This is the generic prediction. Maybe other fields there can be lighter and can be seen, but if you really want to test the mechanism, you need a 1000 TeV collider. Okay? Now, you know, this is why most of the people believe in the community that neutrinos are Majorana fermions, is that any idea starting in 74, where you unify matter or unify interaction like SO10, Patti-Salang, any of these theoretical ideas that have been very popular for a long time, on supersymmetry or without supersymmetry, you tend to always get Majorana neutrinos. And this is why people got very excited, because we like beautiful theories. But you know, for experimentalists, you should not worry about beautiful theory. You should worry about what can you test. You know, because nature, you know, doesn't really care what we consider beautiful. Okay? But this is why for 50 years, people have been thinking that maybe neutrinos should be Majorana, because it's like it's in agreement with all these theoretical ideas. But the depressing thing is that if this is the case, that everything is happening in the high scale, you could discover neutrinos of beta decay. You say, still there is to match this with at the quantitative level to say they are Majorana, but you see lepton violation to Unix, you are pretty happy about that. But from there to say I know what is the mechanism behind neutrino masses, it's a different story. Okay, it's a totally different story. It's not like the Higgs. The Higgs was discovered. You measure the couplings. You see the couplings are proportional to the mass, and you check carefully, and you say, oh, this is the Higgs. He's giving mass to all the charge fermions in the standard model, up to the ones that we have been discovering, because still we don't know the coupling to the electrons and so on, like quarks. But you know, this is how it works. Then now imagine that you are a graduate student and you want to forget about everything that have been doing people for 50 years. Maybe this is just philosophy. It's not really something, nature doesn't really care about that. Typically, if you want to change these ideas, you have to go back. The only thing that we know that is true is a standard model and general relativity. The rest is just speculation. Then nobody has to convince you to learn fancy theory because these are not real theories. Okay? Then, if you want to go back, you will like to see if you can write a theory for neutrino masses where everything is happening at the low scale. Means there is a hope to test. Imagine you try to do something like that, no? Then what you can do is you have to understand the symmetry that we have been talking about all the time, lepton number, total lepton number. The total lepton number is the key symmetry for neutrinos, right? If they are broken into units, you get Majorana. If if it's conserved, the neutrinos are Dirac. Now you can ask a very simple question. You can ask the question, can I write a theory? In the standard model of particle physics, we have the rules of the games are, you have the gauge symmetries. And you have the different multiplet, how they transform. You follow the rules, you grade your density Lagrangian, and you get these accidental global symmetries. Global symmetry that are accidental, where these are local symmetry, right? Then you can ask, if you worry about neutrinos, you can ask the following question: can I write down a theory where this is not a global symmetry, that will be a local symmetry now? Okay, like the others. But the motivation is very strong. Neutrinos are massive, and you want to understand what is going on with that symmetry, and then you want to follow the standard model of particle physics. You want to make that symmetry local and study the spontaneous breaking of that symmetry and see what you get, if you get anything. And maybe it's not even possible to have a consistent theory for that. You have to try, okay? Every time that you use local gauge theories, you face a problem is that there is something that is called anomalies. In the standard model has some magic. If you think about all the gauge bosons that we have in the standard model, let's use the notation, kind of a standard notation. The gluons are typically, there are 8 of them. Let's say A go from 1 to A. The W's, there are 3 of them. B goes from 1 to 3. You have, for this, let's use this notation. And for this, let's use, I don't know, whatever notation you want. At the classical level, what you do, you just write your interaction in the Lagrangian. Everything is gauge invariant. You break the electrosymmetry breaking using the Higgs mechanism. Everything has been done for a long time. But the standard model is more than that. These are anomalies, is that at the quantum level, you can write this graph where, let's say, you have different gauge bosons here. If these graphs are not zero, okay, when you compute they are not zero, you are actually breaking gauge invariance. But you are breaking the symmetry before you do a spontaneous symmetry breaking. Then clearly, this cannot happen. Therefore, the standard model is magic. You cancel all these graphs per family. If you remove, let's say, the top quark, you cannot cancel the anomaly for the third family. Therefore, it's magic that we have the number of degrees of freedoms needed to cancel all the anomalies. Therefore, here, if I put a new gauge boson in the game, means that he can be here, and let's say you have 2 SO2, or maybe hypercharge, every kind of combination, you realize in the beginning that, they are not zero. For example, SO2 squared U1, this means that you have WW here, this W here, and the new gauge boson, these graphs are not zero. And if you get a contribution is proportional to the let's say this gauge boson, if you remember a abelian gauge transformation, I replace the gauge field by the field and a derivative of the parameter that is doing the transformation, the local transformation. You are breaking gauge invariance, and therefore you cannot do a spontaneous symmetry breaking. Doesn't make any sense if already the symmetry is gone. Okay. Then, when you do this, you realize, oh my goodness, now you understand why Patay-Salang was so popular, because Patay-Salang also is automatically anomaly free if you put the right-handed neutrinos in the game. However, it's actually not so difficult. For example, if you put the right-handed neutrinos in the game, these two anomalies are 0. You need actually 3 copies right-handed neutrinos to get this. But still you have to deal with these anomalies here. And then, but you have a very strong motivation. You know neutrinos are massive. And the symmetry that tells you every single neutrino is a lepton number. Then you are not making up any weird symmetry. You see in the archive every day 20,000 papers with 20 different symmetries. Here you are not making up any symmetry. It's just lepton number. You just want to make that symmetry local and study spontaneous symmetry breaking. Then you have to cancel first this anomaly. Yeah? Yeah. No, per generation. We don't have a theory that is able to cancel. You just per generation is cancel. Then you can study this problem, how to cancel this anomaly. Then if you are able to do that, then you can study the spontaneous breaking lepton number. Then I will not go in details, but I spent a lot of time doing this. Even for my surprise, this year I was able to find even the simple solution. And typically how that works is that even in the standard model, right? Imagine you go back in time before the top quark was discovered, right? And you check the anomalies, you say, if I want to cancel the anomaly, I should have a new fermions. Okay, that today we call the top quark. You do this before symmetry breaking. They don't have mass. But you knew before the top quark was discovered that something is wrong with the theory if there is not a new fermion that is able to cancel the anomaly. And then you are so lucky that the top quark was discovered when the right quantum numbers and the whole theory is consistent and the standard model of particle physics is anomaly free, and we can do a spontaneous symmetry breaking. You see how lucky we are, no? Here is similar in the sense that you will need to add new fermions to be able to cancel all these anomalies, and then do a spontaneous symmetry breaking for lepton number. Again, lepton number is a symmetry of the standard model. You are only making local, and it's the key symmetry for neutrinos. Nothing very exotic here. Now, I will not give you all the details, but basically, something surprising happened is that if you want a mechanism for neutrinos, and you want to have anomaly-free U1L theory, you find in the different solutions that there is always a fermion that is there for anomaly cancellation that is stable and doesn't have electric charge and can describe the dark matter in the universe. Then every time that you get that as a theoretician, we call this as a bonus, right? You were not expecting that. Right? It's like going back to Patay-Salang. You want to make your SU4 theory, and you realize, oh, I need right-handed neutrinos. Okay, but they are actually the ones I need for season mechanism. Then it's a bonus that you are getting. A symmetry, it tells you you should get that, and later as a bonus, you realize you can do the season mechanism. No? Here, you will see that this is what is happening. Then cosmology, it's hard to imagine cosmology without dark matter today. And there are strong bounds on how much dark matter you can have in the universe. You cannot do, if the universe is pretty dark, but there's no any number that you want. Then when you do Rayleigh density calculation, you realize that the masses of all these fields needed there, also to the ones that will be involved in the neutrino mass mechanism, they cannot be too heavy because you will get too much Rayleigh density, okay? Then let me give you a feeling how that works, okay? This is a fermion here that is there for anomaly cancellation, and it's stable. If you want to compute the Rayleigh density for dark matter, I will not go in details because it's not a cosmology school, but basically there is a very standard calculation that you have to understand the annihilation of this dark matter in the early universe to everything that you want. Okay, this is this gauge boson here, Cl. Then if you compute all the Rayleigh density, you can make a plot where this is the mass of the new gauge boson associated to lepton number, and this is the dark matter mass. Then if you are in this blue line here, you are getting 0.12 for the Rayleigh density. If you are below, you are getting less. The only thing that we know from cosmology is that you cannot go beyond 0.12 because, maybe the theory can be more complex. But if you want to be conservative with that, but look at that. I can have some peculiar regions here and some peculiar region here. But look at that. If you look to the left, 10 to the 4 GeV. And this is the new gauge boson after you break the symmetry. This guy cannot be beyond 10 TeV. If the symmetry is broken beyond 10 TeV, you will get too much dark matter. But the point is that the seesaw mechanism, or whatever mechanism you are doing here, in this case, it actually, I can explain something later. The scale where you are breaking the U1L, for me, the scale is the mass of the new gauge boson, has to be below the multi-TeV scale. Therefore, for the first time, you have a theory where you understand the spontaneous breaking lepton number, and cosmology tells you that everything should happen at the low scale. Therefore, you could start dreaming about the stability. Because if I tell you the theory is at 10 to the 14 GeV, I mean, it's good to dream, but not too much, right? Because we don't have you cannot build any experiment where you can actually have access to that in a real way, right? Then let me give you a better feeling. Let me give you a feeling, if there are a few theoreticians here, how that works. To cancel the anomaly, you will need the right-handed neutrinos. It's interesting that you need the right-handed neutrino, which, if you get something, maybe, okay, you cannot do anything for neutrinos, and you get this 4 representation here. Here, I am not listing the QCD quantum number because they don't transform on the QCD. Then this is a singlet for SO2, doesn't have hypercharge. This is a neutral fermion, and has a lepton number 3 to the 4. Lepton number is a generalized symmetry here. You don't know what lepton number. They are fixed by anomaly cancellation. You cannot put whatever you want there. This number is fixed. Therefore, the fact that you get a neutral field here, and when you check it's stable, it's amazing that you can make a connection between the origin of neutrino masses and the dark matter in the universe. And this is how it works, okay? I don't want to go beyond my normal time. Actually, I'm okay with the time, which is good. But basically, this is the prediction that you are getting. You can, of course, every time that you write a model for anything, you have to make sure that the spontaneous symmetry breaking works well, that the new fermions, they can get mass, and you satisfy all the collider bounds, and you don't make a mess in cosmology. Okay? When I say you don't make a mess in cosmology, is that we understand cosmology very well. We understand, let's say, BBN very well. You cannot have a theory that is producing, let's say, fractional charged fields that cannot decay to the standard model field or something like that, because they will form exotic atoms and exotic things we didn't see. And then everything in the game, you find you can actually generate masses for this field. You have this particular quantum number for new Higgs, and these allow the new Higgs, the new fermions to decay. Again, it's only 4 extra fermionic fields that you need for doing the job. Then I will go very quick here, but this is a very interesting thing for experimentalists, I believe, because if you study carefully, the symmetry breaking and the spectrum for the masses. This is the mass of the new field. When this new field get a BEV, this is the mixing with the right-handed neutrino of this field. You can compute the mass matrix for right-handed neutrinos, and you realize that this mass matrix has rank 1, and then only one of them will get mass from symmetry breaking. Then at the end of the day, you can get the left-handed neutrinos together with 2 extra light right-handed neutrinos, and you can get a 3+2 light spectrum. Then if this new field get a BEV, this theory is predicting that you should get 2 light neutrinos, extra neutrinos. It's very hard to get something like that from a usual type of theory because everything is happening in the high scale or everything is very complex. Then there is a hope to do that. Of course, there are bounds on that. Okay. Then, or you can have the other case. If this new field doesn't get a BEV, neutrinos can be Dirac. And again, everything should happen at the low scale. Then this minimum model could give you both possibilities, but in both cases, you are getting a very interesting prediction. There are other models that we not discuss, but most of these models, they provide the dark matter candidate for the universe, and using the cosmological bounds, you can say that everything is happening at the low scale. Then for any experimentalist, if I tell you that you are writing a theory that is making a prediction that you could maybe test, that should be always welcome. But if I tell you that I'm writing a theory that is very beautiful, very, very beautiful, it's so beautiful that you never can test, I'm not sure this is the argument that we should follow in nature, right? Everything can be so beautiful you never can touch. Then it's at least as a physicist, I don't find that so beautiful because I can never can test. Okay? Then I will finish in this way. I try to tell you, in the first part, I try to remind you how the charged electrons get mass in the standard model. This is something real. The Higgs is something real, has been discovered. It's amazing that only one multiplet can do the job. I try to tell you that even if we know neutrinos are massive, we have no clue what is the mechanism behind that. In the beginning, I tried to review the 2 simple mechanisms for Majorana neutrinos and what kind of properties they have that allow you maybe to discover them at colliders. However, these are just toy models. You are not able to predict what are the masses of the new fields involved in the mechanism. Then you can, of course, hope to look for them. As an experimenter, you should look for anything that you find exciting, okay? You should not maybe listen too much to theoreticians. But the truth is that as a theoretician, I try to understand if there is a way to predict something, okay? Then these toy models are not able to predict. They have very interesting properties. Maybe the neutrinos are Dirac, and we will need to wait a long time to know about this. And then in the second part of this talk, I try to tell you that a large fraction of the community believes that neutrinos are Majorana, and this is coming already for 50 years. People like the idea of unification or simplicity or theories where you can understand other things about the standard model. And typically, you will get Majorana neutrinos. The only problem with that is that these theories are describing physics at very high scales. And even if you discover proton decay and could give you some information about unification, it's very, very hard because, again, we don't have access to that scale to be able to produce all the fields as we do in the standard model and be able to put everything together and say, this is a theory for neutrino masses. Okay, it's not enough to say neutrinos are Majorana. You need more than that. You need to test. And in the last part of the talk, I try to tell you that there are new type of theories that I personally have been involved, where if you assume that lepton number is like any other symmetry in the standard model, you make that local, and you study the spontaneous breaking of lepton number, you realize that in most of these models, you will get the dark matter candidate. If you want to be consistent with cosmology, this will tell you that the symmetry breaking scale cannot be high. Therefore, this type of theory is opening a new way to be able to be tested. Okay? And then only the experiment will tell us what is real. Okay? But again, every time that somebody tells you that they have a very beautiful theory never can be tested, this is very controversial. At least Richard Feynman used to say, this is maybe not scientifically interesting. But I didn't have time to talk about many things. You are welcome to ask me, but what you are doing is very important, because if you find neutron reservoir decay, it's very important, because this will kill most of the half of the theories that have been proposed. And then we can focus and look, okay, now we know neutrinos are membrana. Okay, maybe we can find a way to test the mechanism for neutrino masses. Okay? You're welcome to ask me any other thing, but I actually will stop here. Thank you. Right, let's go there. Okay, when you have QCD, the gluons, right? Now, when you have SO4, here you go. When you, here you go. When, QCD, you have the gluons, right? Now, SO4. Then the gauge boson live in the joint representation. The gluons live in a 3x3 matrix. Now you have 4x4, right? Then you have the gluons here, and you will get new gauge bosons there, predicted by the fact that your gauge field should be a 4x4 matrix. They are called Bertolletto quarks because they will couple to quarks and leptons. And you get a second gauge boson that is actually also there. This is the diagonal generator of the algebra. And then your answer to your question is yes. You are predicting new gauge boson. In particular, these are more interesting because they are totally different from anything that we know in the standard model. All the gauge bosons that we talk in the standard model, they talk to quarks or to leptons, but these guys will talk to quarks and leptons. And if you find anything at collider like that, imagine you find something like that at collider, you will say, oh, we should have something like SO4 at some point. However, as I discussed, the neutrino provide a huge stress because to be consistent with neutrino masses, everything typically will happen at the high scale unless you have what we did here. You have the inverse seesaw mechanism. Therefore, generically, these new gauge bosons are mediating this ray process, and you have to live around 1000 TeV. But maybe if you find that a collider, things can go around in a different way. Hard to imagine, but maybe possible. Oh. Which slide? Because this one or? Okay, good. Let me emphasize something. Since I didn't want to give you too much details. I wanted to tell you these are the three type of models that people have been able to propose. You had to write a theory where all the anomalies are canceled. You are able to generate masses for all the new fields. You don't spoil cosmology, and everything has to be consistent, no? And luckily, you can have different models. And what I want to say is that in 90% of these models, you always get a dark matter candidate, okay? Now, since I don't have time, it's good to talk about what is the simplest thing you can do, right? For any speculation, you should ask the question, what is the simplest thing to do, right? If you drink coffee, you just drink. You don't go there and come back and drink coffee, all right? And then, let's go there to the slide. I just try to, sorry about the time-consuming change here. Okay, here you go. Now, in this particular, if these new Higgs get a BEV, the right-hand neutrinos, the chi will mix with the right-hand neutrinos. And then it's exciting because when you check the mass matrix for right-hand neutrinos, you realize that this mass matrix has rank 1. Only one right-hand neutrino get mass from symmetry breaking scale. The other two don't get mass from symmetry breaking scale. I am talking the U1L symmetry breaking scale. Then the spectrum is a 2 plus 2 neutrino. And this is interesting because, again, you see, every time that you write a theory and you get something you never expected, because, I mean, you had no idea that you will get 3 plus 2 line neutrinos, it's interesting. Okay, in this case, all of them mix, and this chi is not stable. Now, one has to be more general. If the BEF is 0, the neutrinos don't get any Majorana mass. But then the chi is totally stable, and then you get the upper bound from cosmology. Again, there are other models where neutrinos are Majorana, and there is an upper bound from cosmology. Then everything is happening also on the low scale. Okay, it's just in a talk like this, I don't want to go in more details, huh?
Thank you again, Pavel.
Mm-hmm. Thank you.